So we're in section 11.2. We're going to talk about vectors in space. Several years ago, we decided that should be the title of a movie. Vectors in space. All right. So what we're going to do is just extend what we talked about in 2 dimensions to 3 dimensions. So we're going to make our z-axis, our third dimension, perpendicular to the x and y axis. And the way we normally draw them, doesn't have to be drawn this way, but we usually draw them like so. And this is going to be our x-axis, our y-axis, and our z-axis. And these extend back this way and back this way as well. And down. Vectors in space, snakes on a plane.
Vectors on a plane.
Vectors, snakes on a vector in space. And we call this a right-handed coordinate system, because if we put our arms in the directions of the x and y axis, our right arm lies along the x-axis. So if our right arm if our left arm were along the x-axis, we would call it a left-handed coordinate system. And we're only going to work with a right-handed coordinate system. And what we'll refer to the planes that are produced when we construct our z-axis. So we have the xy plane down here, the yz plane here, and the xz plane here. So we'll talk about our coordinate planes rather than our coordinate axes. Well, we'll talk about the coordinate axes as well, but we'll refer to the coordinate planes a lot in 3 dimensions. And our planes divide space into 8 octants. So we have 4 above the xy plane and 4 below the xy plane. Normally, we'll talk about, we'll only name the first octant. We can number them just like we did the quadrants, but usually we'll just talk about the first octant, and then from there we won't talk about the second octant and the third octant and the fourth octant. So the first octant is here where x, y, and z are all positive. And we will say that x is our distance from the yz plane. And y is the distance from the xz plane. And z equals the distance from the xy plane. So we'll refer to our distances from our planes this way, and that'll come up fairly regularly as well. So any questions about how we're constructing our space? So all of our regular ideas familiar ideas from the plane hold in space as well. Our distance formula is the same. We just have a z term. Midpoint formula is the same. We just have a third term for our midpoint. Our standard equation for a sphere is like the standard equation for a circle. We just have that z component as well. So all of those familiar ideas are the same in 3 dimensions. We just have the added z component. We'll talk about our standard unit vectors, like our joke referred to. So our standard unit vectors in 3 dimensions. Standard unit vectors are I, j, and k, I hat. is 1, 0, 0. Unit vector in the x direction. J hat is 0, 1, 0. And k hat 0, 0, 1. So those are our standard unit vectors in 3 dimensions. And we'll, just like I said yesterday, we will refer to them kind of interchangeably with the bracket notation and with the IJK notation, just so we're familiar with both both notations. And our length or our magnitude of our vector, same definition as we used in 2 dimensions. We just have that third component. And I want to mention, I don't think that we mentioned it yesterday, that 2 vectors, how do we tell when 2 vectors are parallel? So 2 vectors are parallel if one is a scalar multiple of the other. Where C is a scalar. So that's our test for parallel vectors, or one of our tests for parallel vectors. We'll come up with another one a little later. So our vectors are parallel if one is a scalar multiple of the other. So really this is all we're adding today to what we talked about yesterday. The homework, very similar to what was assigned yesterday, just has to do with the vectors in 3 dimensions rather than vectors in the plane. So I just want to do one quick example of a type of problem that you might see that has to do with 3-dimensional vectors. So let's say, before we move on, any questions? Okay. Let's say we have a cable. And this cable, it's stretched between 2 points, I don't know, between a tree and the ground or something like that. We introduce a coordinate system and we find the coordinates of the endpoints of the cable. So our cable is between, when we put a coordinate system here, we say our cable is between these 2 points. 1, 3, 5 and 4, 7, 9. And we know the tension in the cable is 50 pounds. We want to represent the force in the cable as a vector. So, any ideas of how we want to do this? Well, first, let's. What is the 50 pounds? What is that telling us about the force? What part of our vector is that telling us about the force? That's our magnitude. So this is going to be the magnitude of our force, and we need to get a direction. So what's going to give us our direction?
Vector, like transform.
So the vector.
Terminal point.
So we have our points here, so we can write that as a vector, right? Then what do we have to do? What are we going to have to deal with the vector between these 2 points? What don't we want involved from that vector? We don't want its magnitude involved, so we need to normalize this vector. So we're going to, our process is going to be write a vector between these 2 points. We'll normalize that vector so its magnitude is 1, and then we're going to multiply it by the magnitude of the force, and that will give us our force represented as a vector. So vector between the points And it could go either direction. We're not specifying which direction. So either direction for this particular problem would be correct. I'm not specifying that it's going to be positive or negative. So I'm just going to write the vector between these 2 points I'm going to do 3, 4, 4. So I'm saying this is the initial point and this is the terminal point. So that's our vector. And now we're going to normalize it, so we need a unit vector. In the same direction. And I'm going to divide this by its magnitude, so 1 over the square root of 9 plus 16 plus 16 times this vector. So my unit vector is 1 over the square root of 41 times 3, 4, 4. And then our force, we can represent our force is 50 over the square root of 41 times this vector. And there's our force represented as a vector. Going in the direction of the cable, and its magnitude is 50. So there are a couple of problems in the homework where it gives you some kind of physical situation, and it asks you to do some things like this, where you have to represent the force. It gives you points, and you have to represent the force in something as a vector. So this is the process it's asking you to use. Questions? Okay. That's all I wanted to. That's all we're adding today. So that's section 11.2. So first 2 sections of chapter 11, pretty easy. All right. Is everybody feeling peppy today? No?
I am Mr. Beaver.
There you go.